Okay. Что-нибудь вы успели посмотреть из этих? Окей. Ну, okay, let us start. So today we go more back to history. And actually what I wanted to do is to mention several important names. We don't have really time to study things, but I think at least you should know certain names which belong to so-called ancient Greek. Sometimes it's simply referred to Greek, is assumed, understood that it's old Greek mathematics. So I already mentioned Euclid, of course, right? And we spent some time with Euclid looking into his elements. I mentioned Eudox, if you remember, that was a mathematician who actually wrote book 5 of Euclid's elements. I mean, this is a material where we have this geometrical theory of proportions, where we have what we call today Archimedean axiom, right? And certain theory of ratio, geometrical ratio, which equivalent in some broad liberal sense that I'm not going to make precise now, to theory of real numbers. Right, that's those names. And now I want, just a minute, I want to write them, and I think I'm going to write on this screen using my tablet. So no. Yeah, I mentioned Archimedes, right? So I think I will not talk more about Archimedes. Unfortunately, we didn't have time really read at least one of things. If any one of you is interested, one good place to start is this thing about Parabola, which is, very detailed and I think is very characteristic for his style. And it is, by the way, based, as most of Archimedean writings are based on this 5th book, right? When we say that he calculated, say, volume of cone, that it is 1/3 of cylinder and so forth, of sphere, that's actually what is meant. What he did really is that he calculated ratio. For example, that ratio of cylinder to inscribed cone, inscribed into the cylinder, is 2 to 3, right? That's what he really proved. And as I mentioned, he didn't even have this concept of, say, volume. He didn't think in terms of measures as a, say, number, real number, again, as we do it today. And so that should be understood as a ratio of 2, say, solids, right? But of course, it is translatable into modern terms as a ratio of volumes. Actually, that is a big problem. Probably I mentioned that of reading the old texts, right? Because of course, when we read them, we most often, maybe inevitably even in a sense, read these anachronistically, which means that we interpret this text in our today's term. And just check if yes, everything works here. Yeah. Yes, and that's I think both inevitable and even useful, because after all, it makes this old text somehow relevant. We understand them in that way, right? If we say, look, he computes volume, or it's another simple example. Maybe if I give a talk, I just gave last week a talk in different place. It's on my YouTube and on my webpage. You may look up on Euler. It's very, very Leonhard Euler from St. Petersburg, from very popular subject of Königsberg bridges. I guess you know. However, it's even in Wikipedia, you can read that Euler founded graph theory, that it is sort of topological theorem, right? And that's correct in terms of interpretation. But if you look more carefully into Euler, into contemporaries, then topology didn't exist. It just came about at least 100 years later. And there is no actually justification, there is no evidence that he was thinking about anything like topology then. It's true that the outcome is very, naturally interpreted in terms of topology, say in case of Euler, or in terms of volumes in case of Archimedes. However, it's, I think it's his, aim of historian is actually a look into this interpretation. You can give it, it's useful, right? Somehow to just to read this text, understand what they about, broadly speaking. But then you should actually look into differences. And at least in case of Euler, it took 150 yees when people took from this map of Königsberg to this diagram with the graph, right? And that was also history. So people somehow developed this intuition, these new concepts, actually quite independently of Euler work. And so all this, interpretation is also a matter of history, but actually of later history, right? That connects, say, us to volume, or things that I will talk, hopefully today, if we have time, more precisely. Remember, I mentioned second book of Euclid, right? When there is very kind of natural reading of these geometrical theorems of second book in algebraic terms as algebraic identities. But that's the same story, so we can easily read them, and it's somehow a way to understand them, right? And it gives access, if you like, because otherwise you don't know what he's doing. However, if you look, and that's what I'm going to do, you see that nothing like algebra existed. There is no evidence that he did anything that he thought algebraic, right? On the other hand, when algebra rised, and that happened, no, at least in anything like modern form, it came later, actually like in about 1 millennium later. You see, it's quite a long period, historically speaking. And then these people, they used Euclid somehow as a part of their theory of algebra, if you like, right? And that's I show. So, but that happened much later. So, it was of course important. And now, after 1 more millennium, or actually millennium and a half, even, right? If we look on all that, right, we have this optics where it shows us algebra in Euclid, but this is a illusion in a sense, right? It's not pointless. However, no, roughly speaking, it's like, you know, if you use this optical analogy, it's like you look into telescope, right? Even today, actually, people don't usually, they look into computer screen. But anyway, you see something in your screen or just in your ocular, and you should interpret it, right? You should interpret it for saying what it shows you about, real things you're looking at, right? And to be in a position to interpret it correctly, you, first of all, you should know how your instrument works, right? What are principles behind your optical instrument, right? And that's, I think, no, this is analogy or metaphor even, but it's the same thing. So we should simply understand how it's possible, why, how that's historical optics works to show us algebra in Euclid. And that's possible. There is no mystery about that, right? So, right. So what I want to do is, as I told you, to add a bit more names. Good. So, so one name I did mention it, but I recall it's Eratosthenes. Really? Probably I shut down. Sorry, it takes time. Stop video. It gives a little bit more power to my poor computer. Eratosthenes of Kyrene. So it's standard that's along with the name of a person, people mentioned where he or she comes from. So it's Kyrene. Right. His year that C, you know, it means circa in Latin, which is about. So precise dates are not known. So circa, you may look also Wikipedia in English, it's pretty good, I think. So that's some approximate years. So it's of old year, right? BC, before Christ. So that person, from that person, we don't have actually extant writing. That is a bad thing, right? However, we know that he was extremely influential. I mentioned that he was one who calculated the size of the Earth very accurately, and he was a poet. He was a chief librarian in Alexandrian library, so he was kind of like president of Academy of Science or something, right? So he was extremely influential. That's there is a lot of mentioning and some fragments and so forth, but we don't have writings. Actually, there are at least two kinds of people who kind of important, right? And that's first kind, which means that we don't have any writing, right? And actually, for quite a while we don't have, right? So usually what survived, say, Middle Ages, it came to hands of today's historian, not in all cases, but in many cases. But these writings were lost. No, I'm not an expert on Eratosthenes, but you may look quite long ago. But we know a lot of mentioning, so I think that's an important name. But probably second group of people is more important in a sense. And second group is these people were not necessarily very influential among their contemporaries. Okay, no, at least we may not know about this, right? We don't have many mentioning of this name and so forth. However, for some reason, his writings are extant. They survived, right? And survived again, it usually means that it's for long. It's very rarely now happens that there are, say, certain archaeological findings, right? And people, even there are such events, I already mentioned, I think this Archimedes palimpsest. So when we really discover, dig out kind of new text that was not, what is more often happens, of course, is that certain text was copied and recopied, and there should be some reason for that, right? So a person might be not influential, say, in his time, or at least we might not know nothing about that, how he was or was not influential. However, for some reasons, certain piece of writing was republished, rewritten, and commented upon, and so forth, right? And that, we might say that a person becomes important after his death, if you like, right? That's he has this long post kind of afterlife, right, which comes to our hand, which still continues in a sense, right? No, there are actually mixed cases, right? And I think my next name is a rather mixed case, because he was influential, at least there are many mentioning. So this guy is a contemporary, more or less, of Euclid, right? Eratosthenes is contemporary of Archimedes, by the way, and even they locally were in the same Alexandria. And next person I want to mention is Apollonius. I think he was sufficiently influential, at least in the sense that we do have many information of him among his contemporary sources of Perga. Right, so years circa 240, so it's 3rd century. Yeah, so you see it's almost contemporary. Yeah, and he is known mostly for his, actually it's quite thick. If you look, it's 3 thick volumes of his conics, right? So he's writing about conic section, which I even didn't try to study with students like that, because it's really hardcore. I mean, and somehow Archimedes is easier, maybe it's better published also, Archimedes, better commentaries. That's, I think, I'm afraid I'd be mistaken, but I think it's the last academic publishing, I mean, of original text. It's still from 19th century. And that's really hard reading. All right. However, just as a mathematician, anybody easily can prove, right, that or not. You know how, say, conic sections are defined as conic sections. So you have a
intersections and planes of a cone.
Yeah, exactly. And can you easily, and by the way, in Apollonius, this cone is not orthogonal, it's general cone. Oh, right?
What is
orthogonal means that this axis is orthogonal to the plane of the base, to the base. It may be not orthogonal. This is also a cone. That's it's not a matter of how say of this base, because I assume that the base is a circle, right? Now, base is a circle. And this is a, I don't know how it's called, a rectangular cone or something, orthogonal cone, something like this, right? But you may also move this, have a different angle here. And that's kind of scalene cone. So all the theory works actually for scalene cone as well, just as for this orthogonal cone. And basically you have 3 kinds of section. So either you intersect with the plane which may be parallel to the base, then you get just a circle. But if it's not parallel but still intersects both sides, right, you get an ellipse. Okay, then you may intersect by plane which is parallel to axis, parallel to right to his axis, right? And then you get what? Then actually you may have also second. You get to think of two topologically disjoint parts if it's parallel to the axis, right? And do you know how it's called that? I guess you do. It's eh? It's called hyperbola. And actually, you know this terminology, hype means smaller than, right? And hype, it means bigger than, I'm sorry. Ellipse means smaller than, all right? So they are calculated. And third option, different option, if you make your plane parallel to this по-русски это образующее generator line to the side of the cone, and that will be different. It will be no longer hyperbola. And what it will be? Parabola, right? And parabola, you get just one piece. It comes with one piece, like this, something. Huh? So parabola. So this is ellipses.
How did we get hyperbola?
Sorry?
How did we get hyperbola?
Hyperbola, you parallel to the, it's called x, to ось, axis. But you have axis. No, it may be orthogonal to the base, but not necessarily orthogonal. And you get a plane parallel, but not going. But your axis is not on the plane. If you get on the plane, you get the like triangle, right? If you just making plane and your axis is in that plane, then you just get triangle. Or if you continue here, you get like two triangles like this, right? However, if your is parallel, then you get these two things, which is called hyperbola. And the terminology somehow parabola is seen as a kind of base case, right? And then you have a smaller and bigger angle, basically, right? So if you move your plane from parabola one way, you get ellipsis or circle as a special case, or if you move it in that position, which makes it parallel to axis, you get hyperbola. That's the theory. That's the reason why they are called conic section. And as I think I told it last week, basically they consider this conic section be three-dimensional objects. You see, that was part of stereometry. So that's idea that those are plane curves, right? That the two-dimensional object. Basically, it comes only with René Descartes. No, probably today, probably next week, we already will look into René Descartes, into his geometry. So he really rethought it, right? And basically, again, they were not thought as a curves. No, actually, they might have this idea in some ancient sources that these things are generated. That actually knew that, you know how one may generate an ellipse. Just take 2 points and have a thread with the constant d1, d2, and d1 plus d2 is constant. So you have like ниточку. And if you move it, this point, that becomes an ellipse. So it's what called, in English, by the way, it's called locus. Means, по-русски это называется как геометрическое местоточие. In English, they use as Latin locus loci, which means it's place. No, actually, today we tend to think about this set theoretically, but this concept of locus existed without this set theoretic rendering. But the idea is there is a place where each point satisfies certain condition. No, say you may describe a circle as a locus such that each point just is on the same fixed distance from fixed point, the center, right? And similarly, you may describe ellipse in that way, a bit more complicated. But this was in kind of secondary because primarily those things were thought of as conic section. Here's the name, and it's more than the name. It's a concept, if you like. You see? Yeah, but now just for you as a already qualified mathematician, just prove. Of course, you know what is hyperbola, what is parabola, like in modern terms, like in terms of equation. But just prove that that is equivalent. You see, it's quite an exercise, and particularly in general case where cone is not orthogonal. So normally you would make it in orthogonal coordinates, right? But then to prove it would also, you would also work for non-orthogonal, you would need to consider kind of coordinate transformation, and which is kind of messy. You see, in a sense, that is an advantage of Apollonius, that he just treats this general case. And arguably, when we do it in Cartesian orthogonal coordinates, that's say something more artificial, because we're just making this special case, and then we should generalize it. So, well, there are probably, I don't know, ways to do it kind of coordinate free way, kind of vector calculus. I didn't try, but should work, I think, theoretically. But I'm just saying it's not immediate, I guess. Maybe for you it is very immediate, but I think it would take some effort. It's not, of course, a really serious mathematical problem, but it would take some time. By the way, if anyone would show how to do it easily, I did it some years ago in a rather messy way. Maybe some of you show some simple way to do that. It would be nice. Yeah. Just for saying, it's again, it's not very easy reading this 3 volumes of this conics. And then, of course, it's all geometrical, you know, there is no equations. And of course, you may translate it again here, of course, that problem of interpretation, that we may translate it into, say, coordinates and something we are more familiar with that, but we may also try not translate, and and perhaps there is something interesting exactly in that part, because when we translate it, after all, okay, we know that it's all translatable into, and so what. So interesting thing may be exactly about how it can be done. Otherwise, probably we didn't think about it earlier. Okay. So far for Apollonius, just to mention that such a thick work as conics exist. There are also some other writings. I'm not giving you full list of writings. I don't have it in my head, and just give you most important writings. So next name on my list, which I think you know, even if you don't know about the person, is Diaphanters. You should know Diaphantian equations, Diaphantian analysis, I think it's called. And that's called from a person, Diaphantus. Of Alexandria, and that's already, it's the same Alexandria, but it's very different time already. Alexandria. Okay, because years are about, this is a much less known, because this person, he clearly belongs to my second class. So it's already new year after death of Jesus Christ, right? It's 3rd century, but not minus 3rd century, but plus 3rd century, much later, and very, very near to nothing is known about his life. He's not mentioned anywhere, but for some reasons, his book, which is called Arithmetics in Greek, written in Greek, arithmetic, it's survived, was read, commented many times, and I think first book of it is lost. However, the major part of it survived. Talking about popular things, a copy belonged to Pierre Fermat in 17th century, and it's on margin on that book that Pierre Fermat gave his generalization, say, of Pythagorean theorem and wrote, I know how to prove it, but I don't have enough place here to write it down. And then it made all mathematicians kind of crazy for 300 years. And as you know, the history somehow came, so the conjecture was proved in late 90s, I think, right? By Andrew Wiles. You may know there is a lot of nice, popular book about this. And I think he first contained a mistake, someone found mistake, then he corrected mistake. So now it's officially proved. I mean, Fermat theorem now, it was used to be called the Fermat theorem. I don't know why, because it had to be called Fermat conjecture, of course, but for some reason it was referred to as a theorem.
Fermat's last.
Yes, Fermat last theorem or Fermat great theorem sometimes. However, the proof that we got with Andrew Wiles, for one thing, it certainly was not what Pierre Fermat could possibly have in mind, simply because it uses a lot of contemporary machinery in algebraic geometry. I made several attempts to understand kind of idea of this proof. At a certain point, I felt I understand it more or less, but of course, right. I'm not an expert. It's rather complex proof. Still, it's a good question, a question which is open, and it's actually not clear it's really a mathematical question or not. Something like, is elementary proof possible or not, right? For example, we don't know whether it follows from, say, piano arithmetic or not. From Gödel first theorem, we know that it might not follow from piano, right? It's a possibility. However, what about this particular proof? There is one paper with the analysis which actually shows that to make it clean, you need kind of even couple of inaccessible cardinals. So it's not even in set theory, it's stronger than usual Zermelo-Fraenkel set theory, and moreover, it's stronger than piano. And so it's open question. No more, say, a less logical question, just saying whether is, in some sort of possible kind of elementary proof, because that proof that is officially accepted as a proof is not elementary at all.
What are we talking about? Proof for what?
For Fermat theorem. If you're interested, you may look. It's called Colin McClarty. He made this analysis. No, it's one L. I'm sorry. Colin. He had this paper on Fermat McClarty. McClarty. I don't remember exactly the title, but it's an attempt of kind of proof theoretic analysis of this existing proof. And which of course, you should also understand that such analysis is also how to say, it's not definite, because if you have one, well, say, normal proof, which logician would call informal, right? But that's just normal mathematical proof, kind of thing that Andrew Wiles produced, right? And then you want to say how it looks like from kind of formal point of view, right? For one thing, you're really not in a position, it is not what Colin is doing, really rewrite it formally. That's simply not possible. And that's, maybe I'll talk a little bit later, is a really weak point of, say, current foundations, because it's all just shows us a possibility. When we are saying that, say, Zermelo-Fraenkel set theory is foundation in mathematics, right? It's just in the sense that it's theoretically possible to rewrite every mathematical proof in terms of, say, derivation in Zermelo-Fraenkel. And there are some reasons for that, right? But these reasons, actually, they are all kind of informal, because what is involved, you get your proof, right? And you should kind of rewrite it set theoretically, and set theoretically not in kind of Bourbaki style, which is also informal, right? But in really this kind of hardcore logic style. And so the best you can do is say that's possible and give some, let's say, reasons for that, that perhaps could be even compelling and kind of mathematical reasons. But what you cannot do, certainly, in any case, except some trivial toy example, it's really do it. It's just say, here my Andre Wiles did as he did, right? Published his papers, and here is my formal version of it. That's doesn't happen.
Why?
Because it's no, roughly speaking, it's too long. It's there is also a nice paper. It's actually in my my paper that I recommended you to first lecture, whether One Mathematics or Many was published in this handbook. I refer there to that paper. Then people try to to estimate size and complexity of this Bourbaki style proof. So you know how Bourbaki works. Already, I go ahead. I didn't say who are Bourbaki. Okay, I'll tell you later. But now just think about it as a project, how to formalize mathematics. So Bourbaki, they give you in first volume a version of set theories, actually not Zermelo-Fraenkel, it's their own, even in a sense more formal than Zermelo-Fraenkel, but this is just, say, calculus. But then later, when they treat algebra, whatever, some part of analysis, they don't use it. They simply say, they use kind of informal, naive set theory, but they have that argument that all that naive stuff can be theoretically translated into this precise syntax. But it's so far so good if you think about this as a theoretical possibility, which is not pointless. I'm not saying that's point. However, if you want to think it, say, practically, it's absolutely out of reach. It's something like 2 times 2 equals 4 would take, I don't know, 200 pages, and anything interesting make it absolutely untreatable. However, in addition, these things are not specifically computable. You know, Zermelo-Fraenkel is not designed for computer. So you may implement them, try implement, but that goes not straightforwardly, to say the least. You know, that's no basically. For example, this all proof assistants, they use kind of type theory behind them, right? There is no type theory in standard set theory, formal set theory, right? And then, so again, that is a big, there is a huge gap between what you argue you can do as a theoretical possibility and things you can do, say, in terms of computer code. And actually, you know, before modern computer came, it's kind of a paradox. It was less clear. People just reasoned like, okay, 1, 2, 3, say, etc. They too easily say, etc. They would say, since we can do that in some very, very elementary case, and there is in principle the same thing everywhere, so we can do everywhere. And with computers, it's actually computers showed us that these resources are much more limited, you see. However, they are fast, big, but real message from computer that resources are very limited, even with this, and we much better see it with computers than without computers. You see?
An example.
Huh?
You have an example, I don't understand.
No, write me email, I'll send you, I don't have a paper, then there is very nice people, then people analyze. No, what you don't, you understand that you have some, I don't know, take not Fermat theory, take some simple theorem of, I don't know, Lagrange theorem of, in group theory, something like this, right? And you have it in Bourbaki, when you have this kind of semantic definition, and then you have a certain idea how to rewrite it in terms of derivation in, say, Zermelo-Frankel or Bourbaki own set theory, right? But okay, sit down and write it. And then you show that you would need maybe not 100, but absolutely inaccessible numbers, say, of lines or anything. And you have no way to control it, because it's not, again, designed to computer. If you want to make something computable and proof assistant, right, then you should invent kind of translation from that language to, say, your proof assistant like Isbell, for example. They, in that direction. So they think about set theory rather than, say, some type. But still, if you look into details, you see that there is a lot of, there is kind of interface, which first involves certain choices. There are more than one possible interface, right? There in many points, situation is kind of not canonical, right? And then again, it's still out of reach to make it easily and you know, word feasible, so it's not feasible. That's it. So what Colin McClarty is doing, feasible. Кстати, по-русски у нас как-то нету, да, стандартного перевода. А? Ну, что-то типа, да. Feasible, not feasible. So what Colin is doing, of course, he cannot possibly rewrite it really, this proof, but what he can do, just take this theorem and kind of estimate, right? What this hypothetical formal version would involve, right? What it requires. And as I say, he comes, maybe it's not uncontroversial, the conclusion that it involves more than, you need a stronger theory to support that kind of really than usual set theory. That his conclusion. But again, I say that is not very, it's not a mathematical theory. That's kind of judgment, you see, because it's very much depends on how you interpret this and that. And so from that point of view, we a little bit came out from our historical topic. The question whether or not there exists elementary, however you make it more precise, proof of Fermat theorem is open. We don't know. And I don't think, at least myself, it could be, I don't think that we may have kind of strong and really convincing meta theory, which would tell us that it's totally, say, possible or not possible, that kind of thing. I think we rather need to have it really or not have it, and we don't have it for the moment. So in that sense, it's not, how say, the end of the story. So there's lot of room, and of course it's not interesting even that particular theorem because it involves so much around. So that's what makes it also interesting, right? But Diaphanters, of course, is important and famous not only for Fermat theorem, right? There is a important result. Maybe you know that. I think it was some problem of Hilbert, proved by Yuri Matiasevich here in his youth about that certain Diaphantian equations. You know what Diaphantian equations are, right? So, no, roughly speaking, equations which you solve in integers. All right, that certain class of such equation is not let's say computable. You can have an algorithm for solving them. That's important result, and perhaps is some of you specialize. There is a lot. I think it's still research going on in this Diaphantian arithmetic. So on. So again, a person which is absolutely obscure as a historical person, with no near to nothing that's about his whereabouts. However, he became and still remains very important. No, except that today maybe few people look into this original book, which, by the way, is pity. There was a Russian historian of mathematics. She died maybe 15 years ago. Bashmakova, I forgot her name. It's a shame. I met her when I was very young, and she actually Russian edition of Diaphanters is thanks to her. She did that, and she wrote very interesting commentary. Somehow, exactly in this kind of anachronistic reading. So she actually never studied that in bottom, but she kind of discovered in this text kind of modern algebraic geometry or something. I think one should maybe read. So it again maybe not uninteresting even from contemporary point of view. Again, look to this historical text. No, I kind of read it. Some parts I never studied it a lot, but that's again I think at least at the level of some drop naming, Diaphantus' name is also very important. And actually there are two more people on my list. Another person is Claudius. I guess you know the name. No, I write Ptolemaios. That's in Greek. In English, you would say Ptolemy. In Russian, we say Ptolemy. Yeah, I guess you know the name, right? Or it's new for you? Really? Okay. No, here I think it's not like Euclid. So he's no. The thing is, more often he is listed not as a mathematician but as an astronomer. However, I think there's not much point distinct even in this Plato classification. Quadrivial astronomy is a part of mathematics, special part of mathematics. So his best known writing, which is also survived, and it's called Almagest. Almagest is actually Arabic name, and I don't know Arabic language. I think not. But when I was teaching in Paris, I always had a lot of students with Arabic, and funny thing that young people like you, right? They usually read all Arabic because they read the Quran, and so I cannot read very old Russian. That's much worse than Latin, Greek, or anything, right? And these guys, today's, they even not necessarily from very, I don't know, educated families, they easily read very old Arabic. So I could always consult them about these old documents. Yeah, so Alma guess.
Arabic common in France.
Sorry?
You said people
In France, yes, yes, yes. I used to teach there for 10 years.
Or do people there know Arabic?
I had students of Arabic, say, origin, who would help me greatly to read this old Arabic. Yeah, so Almageste means something like great, right? Original, Latin version. I actually didn't write down Greek version, called something like mathematical syntax or something like this. That was original title. Yeah, mathematical syntax. But then the thing is, probably I should say it later. No, I can say that later. You know, that's at least European history, and we are talking mostly about European history. And I feel a little bit, how to say, not good that I know very little about, say, Indian and Chinese, and I'm not alone like that, right? I think now a lot of works, and I think that's indeed very important to somehow bring into history of mathematics, more general history of science, to make it less Europocentric, so to speak, right? To have really more global picture, including China, India, and at least these two, right? However, if we talk, so I think we should talk about this European now as a kind of local thing, right? But still, if we are talking about this local thing, it's has kind of special structure, right? This European, and this special structure is this, that at a certain point of history, I think basically it happened what in a standard historical scheme is called by French name Renaissance, which in English means, in Russian we also say, in Russian we say also Возрождение. In English, I think it's Renaissance. It's
Yes.
no English word.
Renaissance is also a word in English.
But it's French, because in English you have to say something like rebirth. In Russian, we say rebirth in Russian, but English just use French word for this. Naissance, this is birth, all right? So it's like rebirth, okay? No, okay, that belongs probably not so much to my course. It's part of kind of general history. And I'm not very, how to say, strong in these general historical concepts. However, I think it really reflects a lot and something important about, at least, probably we shouldn't think about this in global terms, but if we think about this in local terms, it still remains very important. So at a certain point, people somehow thought, and that's in different eras happened in different places, something like late 12th century, 13th century, 14th century, or maybe 15th, the latest, right? 16, it's already a different story. Say late 12th century. So people felt that there was some kind of lost civilization, right? There was a lot of knowledge lost, and that's reflected reality in a sense, right? So if we take Archimedes, for example, it's such high level of mathematics, which it's difficult to say, right, how we measure this level kind of universally, but still, if we are kind of flexible and liberal about that, it's still rather obvious that such a high level of mathematics, as we know, say, in Archimedes or even in Euclid, right? was not reached in Europe until, I don't know, let's say 17th century, until Newton or something, right? So it's more than one, several generations, even many generations of people, they were thinking about their efforts, not as say, doing something progressive, but as a rebirth, of science. And so part of this rebirth was historical, right? So they somehow found this old text, and that's the only reason we have them now, right? So now we succeed just this work. So they found somehow these older texts, they translated them into what in Europe was a kind of international scientific language, was Latin. They studied it, and they somehow built upon them, right? They interpreted them, did something. However, very important part of it, right, was by so-called Arabic transmission. So in a period roughly from 7th to the same 12th century, about 5th century, was really kind of very cultural and scientific life and booming in so-called Arabic East. Actually, at least again to my Arabic students, they would hate if I would call it Arabic, because actually Arabic was just language, just as now we are doing English. They used Arabic as a scientific international language. By the way, person I'm going to talk, he was not Arabic. Once I called Al-Khwarizmi Arab, they were going to kill me because he, of course, is Persian, and that is a huge crime to confuse. So, but somehow in now I think it's also changing. Now I think they more call Islamic culture, Islamic blah, blah, blah. And so a lot of these documents, they came to Europe first from Arabic. So first, say, translation of Euclid were from Arabic to Latin. And later, they discovered Greek originals, and there were new translations from Greek. And actually, this so-called Arabic part is extremely important and still not fully researched, So there is a lot of important research going on that now, but it's there are some specialists. I don't know Arabic word, so it's a big miss on my part, of course. No, however, it's difficult to know everything, Yes. So that's, by the way, case of Ptolemaios. Of course, his first, his major writing, Almagest, was first translated, I guess, also in 12th century. I don't have it here, from Arabic into Latin, and only later Greek text was discovered. Now we do have Greek text in some form again, right? Because when I say we do have Greek, no, I try to explain it more details in case of Euclid, which I personally know better. This is a reconstruction, right? Of course, kind of philological reconstruction based on comparison of different sources, including those Arabic sources, right? That's some people, for example, kind of translate back from Arabic to Greek, and that's kind of important source also, right? That should be understood. That's all these texts there that we do have. They are hypothetical. It's a product of efforts of scholars, of philologists, and that's quite a science. And today we have much better, say, physical methods for dating of manuscripts and etc. And it's quite a lot of work. And at least for this so-called Arabic, in Paris, there is a huge building called Institut du Monde Arabe. And then you have a huge library with huge lot of writings, and there is no people, no money, I would say, to research it, to publish it. And of course, that's, by the way, I was told by a friend with Indian sources, and he was talking about, probably it's in Tamil region. There is also some huge library with some small manuscripts written very small and very special technique, which is huge. No, perhaps it's not so huge in terms of, I don't know, terabytes. If you really digitalize it, it could be somehow manageable by today. But thing is that no people direct, like maybe 10 people hired, and what they can do, it's very, very little comparing that what can be done, at least to publish this text or whatever. So unfortunately, there is less money than historian would want for that kind of research. And that's of course urgent, because many such things can be lost, just lost. Oh, by the way, if you wanted one story that I was told about St. Petersburg, several people, you know, this library, right? It's called the main library on Nevsky, right? And so when it was constructed, was kind of revolutionary event in Paris, and there were several kind of metal containers with some Celtic manuscripts brought here into St. kind of saved from revolution tumult from Paris. They were sitting before in Paris and brought here. So that's what beginning of like Catherine the Great times, right? 18th century. So they were actually brought before library was opened 1 year, and they spent at least 1 year just under the snow like that. Then library next year was opened, they were taken in, and they are still sitting there, and there is no sufficiently time and people to classify them. And I was talking with the colleague who actually it is written in kind of coded Latin, and she told me, I knew, and actually she told me about 10 years ago that she knew about 5 people in the world who know how to read it. Sometimes only some people I allow to come in and look and close and go out. And so she did it. And she told me that she knew like 5 people in the world who can read it. And she told them, I'm the youngest. And she now is 80. So, you see, so, yeah. So if you have sometimes some influence and money, just bring money to historical research. And of course, there are young people who are always interesting. So if there are some money, you can hire, I don't know, students, postdocs, and do stuff about this. But that's just needs decisions and will and everything. Yeah, so that's just for Ptolemy. No, it's okay. It's edited. So that's, he also had a geography, which unfortunately is much worse shape in the sense that it's much less extant, only parts of it survived. So it's, unfortunately in Russian, we don't have this geography translated or published. I think this we do have Russian translation. Yeah, and that is astronomical. I think I explained to you about epicycles. That comes from Ptolemy. So it's no, you may compare him to Newton in the sense that it's mathematics, but kind of astronomical mathematics, right? So he develops, he does some new mathematical stuff, and basically it's about what we would call today is spherical geometry. You see, so that was quite developed subject, is not in Euclid because it's supposed to be like more advanced, but actually one name I didn't list it this morning. It's Menelaus. Also, you can check his name. I think it's lives. I think it's like this, or just try to Google it. What Google, maybe it would correct. So that's important. Also, author for spherical geometry, but I think very also little survived of his text, unlike Ptolemy's. Okay. So last name on my list, which actually will make me some connection to 17th century later, is Pappus. Of course, there are much more names. I just give kind of important names, right? Is Pappus. Pappus. In Russian, we just say pap. I don't know why. It's actually funny. Plato, for example, we say Platon in Russian, and Platon, you know where it comes from. It comes from genitive, because in Greek we would write sorry, something like this. His name, Plato. That's Greek. So when you say Plato in English, it's closer to Greek. However, in genitive, предикум падеже, it would write like this: Platonis. And in books, why genitive? In books, if you have, let's say, title and name of author in genitive, it means who wrote it, to whom it belongs as an author. It's like genitivus possessivus. And so at a certain point, I don't know exact story, but Russia now, they just accepted that genitive. They probably thought that it's original form of the name. So that's why we are saying Platon rather than
How much
Plato.
How much cases have Greeks?
6, one more than it's also had vocativus, vocative, and as in Old Russian, and actually vocative exists today. No, my girlfriend is Marina, and I say Marin. It's not maybe officially recognized, but it's clearly exists. Huh? Звательный. Okay. Okay, so Pappus, also he called his official name of Alexandria also. So his years like this, so he more or less contemporary, no, sorry, not contemporary, a bit younger than Diaphanters, one generation younger. So he's youngest actually on our list. His author, again, I think near to nothing is known about his whereabouts. However, there is a rather thick, voluminous text called Collection. Actually, original name is, no, I write it in Latin letters, is synagoge. Like today it's used for Jewish church, but actually that means something where, I don't know, something comes together. So that's one of the meaning of these words is also, it could mean like a church where people come, but it also means simply collection. Yeah, and that's rather interesting text because it's, you know, it's, no, sometimes this text is referred by historians as an evidence of kind of decline of, say, Greek mathematics, because it's nothing like Euclid. There is no deductive order. It's kind of a mix of theorems, a lot of things without proofs, if not most things without proof, and a lot of kind of, I don't know, reasoning stories. But I find it actually very interesting, also very good, very rich. And that text that was very influential on at least since this Renaissance time. Particularly was important for Descartes. We are going to look into it. And today, of course, it's not very widely read. Is nothing of it is widely read now, but it's very important source of, even if it's you see, rather late source, but still very, I think, interesting and important. There are many stuff. I will come actually back to this collection when we talk about Descartes and analysis synthesis. No, yes, I think so. If we need to close this chapter, I think I would close it. So that's roughly Greek mathematics, right? Even I remember well one of my professors saying that's kind of cultural history. Maybe you know, in certain point he was rather popular. Sergei Averintsev, he made this remark, which in a sense rather obvious. However, I remember that it's kind of struck me then. So he told this whole thing when, you know, the standard 19th century scheme, maybe even earlier than 19th century, when people say, okay, this is antiquity, Middle Ages, Renaissance, and say modern times. I don't know. Then it comes already close to us. And then he made this remark that before Renaissance, people had no idea that antiquity ended and that there was some like Middle Ages. There was no such conception. It's only when people, and that's on the other hand, that's important, kind of cultural phenomenon that many people, and that applies not to mathematics in particular, but also to, say, theology, to medicine, to everything. They somehow felt that we should give new birth to that. There is kind of lot of forgotten knowledge behind us, right? And so we should somehow study it, give new birth. And that's at that point they invented that scheme, that there was kind of golden age in Greek science, and then kind of unclear Middle Ages, and then it comes to this Renaissance. So, but anyway, in the same modern times, in 17th century, we will see it saying in Descartes, people would talk, and that was common talk about, for example, ancients and moderns, like meaning ancient authors and new authors. And that was kind of important disposition, I would say. So, and sources from the so-called ancients, right, or Euclid, or and Pappus was among these. Okay, so I think no, as I say, of course, there are a lot of things. Of course, what sometimes called as Greek, you see, there is many different periods. Is a period of at least a millennium, which is a lot of, right. So the earliest, whatever, Pythagoras, right? It's presumably some like 5th century before Christ, right? Then we have Euclid in 3rd century. And then we have these people, maybe latest, and we're talking about mathematics, latest is probably Proclus, I mentioned. No, basically he's not mathematician himself, He's rather whatever philosopher, even theologian. However, this commentary that I mentioned, Proclus. So he belongs already to 5th century. It's 400 something, right? It's extremely important commentary to Euclid. Commentary to Euclid. Among other things, because it contains the only extant fragment of history of Greek mathematics written in a roughly Aristotle style, and that's the only, no, at least the most important place where it's found, but not only because of this. So roughly we have this millennium of Greek science of Euclid, and then of course there is a interesting but say more specific, and I'm not an expert, and there are very few experts in that, of kind of early Latin translations, right? Not European Latin translations, but early, some translations were made by Boetius, you know, it's also already Roman. So sometimes historians make some general judgment saying these Romans were not so much interested in the real science, but I am kind of very skeptical about this general judgment, so I don't know. No, the truth is, on the other hand, that you see even important writings like Pappus were written in Greek, right? So at that point, Greek remained kind of scholarly language of culture. So people would study Greek. No, even of course there were important attempts to write something intelligent in Latin too, like that is De Rerum Naturam. What's his name? Virgil, Lucretius, who was we may say poet, but he was actually a scientist. So he actually was educated in this Greek education, but he wanted to do it in Latin, and that's very, very interesting. I'm afraid to confuse the century. I think it's 2nd century or so. You may check. Lucretius. So it's one of actually a few examples when people not simply studied Greek, right, and read Greek and produced or written something in Greek at that time, but tried to do something intelligent in Latin. And that's, of course, his case. I think it's called the Rerum Natura, о природе вещей. Yeah, and that is great thing actually. So you have it's kind of physical. It's a physical treaty. No mathematics there. Maybe I should mention, yeah, of course, but it's all in Latin verses. So it's like you would have I don't know, Landau Lipschitz or something, but in poetry. In a sense, it's a great also ancient text. I think at least I read almost all and quite enjoyed it. Okay, so I think we have like 15 minutes, but I think it's enough. So I kind of close a chapter. So next chapter is actually, I'm making kind of huge historical leap. Okay. And now I want to talk about a person who lived already Oh, I didn't put his years here. That's a shame because I think it's 7th century something. So I write his name. If anybody can just Google and look his dates, because I'm really bad at remembering dates. I'm sorry. Muhammad ibn Musa al Khwarizmi. Yeah. So this Khwarizmi means in Russian we call it Kharezm. I don't know how it's exactly in English. Ага, спасибо. 783. Ага. Yeah, so it's 9th. 783, 850. Ага, спасибо. Okay, yeah. Yeah. So that's actually not a city, it's a region, and it's a contemporary region. Part of it is in Uzbekistan, today Uzbekistan, and Uzbekistan is actually recognized as a region, oblast, however they call it today. Historically, it's very important. It's a very long history. I just looked. You may just Google Kharezm or whatever. There is a lot of. It's very cultural place, and used to be in that time. So it's 8th century, and actually, when I think now, it makes me a bit sad and pessimistic because you see how places they were just full of culture and science and everything. In a sense, they decline into, I don't know, poverty, dictatorship, etc. So unfortunately, today is much easier to imagine some real intellectual advance in these places, but that was the case at that time. Okay. No, by the way, just his importance, for example, comes al, if I understand correctly, also means something like genitive, from, right? That means he just from this place, but that's name that from Khwarezm, al-Khwarizmi gave birth to other common word algorithm, for example. That just kind of form of part of his name. And that's it. And the name algebra is also kind of modified title of his treaty, which means roughly completion and something like completing and balancing. Right, and that's, I hope we are going to look into a little bit, and balancing, and that refers actually to some simple rules of algebraic identities that we all study in elementary school. Right? But that, for that time, that was very new. So why I somehow focus on that name rather than any other? No, because one thing he is probably and was even, say, in 12th century, say in Europe, better known. Probably he was the only so-called Arabic author known in Europe in 12th century, because those books, they were translated from Arabic to Latin in late 12th century. And by the way, some of these manuscripts are very well preserved. Actually, there are two key manuscripts. One is sitting in Oxford and another in Cambridge. And one of these, by the way, were made by kind of Englishman. It was Robert of Chester. So it was, and another was someone from Girona, who I think French would claim that he was French, but of course, nothing of today's national state existed at that point, so it's rather pointless. Anyway, why he is important? No, some authors, probably I tended to believe this myself, but now I recently was a big congress this July, supposed to be in Prague, but after all was just on Zoom, of historians, and actually some people like Leo Corey, I believe him. For me, he's a really big authority. He told me, no, you shouldn't say that. But another important person who is called Rushdie Roshed, who is rather old, Rushdie Roshed, who is probably, except with Leo, the best living expert on this so-called Arabic mathematics. He works in Paris, in France. He believes that really this guy Al-Khwarizmi really invented algebra, that it was kind of one-man invention. Like, I think if there are even Leo kind of convinced me that no, that was wrong, that there were some absolutely unknown sources that made something similar, and that of course is much more realistic than that idea that one person would invent it. But at least, say, from this historical perspective, right, Europeans knew about algebra from one source, and that was the source. So in that sense, maybe, and algebra, of course, it's something very special. That's what, I think we are coming to close, so it'll be next week. In all this Greek mathematics, again, the second book of Euclid, of course, no algebra, that's just interpretation. Some stuff in Diaphanters, for example, they look very much like algebra because we have equations after all right? But still, these things are, I would say, rather a matter of reading, right? And as we shall see in Al-Khwarizmi, just leaving aside question of his sources, what he's first, not first, but at least in him, we find this kind of idea of algebra. Actually, Rushdie Rashid, he published a paper which called The Idea of Algebra about Al-Khwarizmi, where he claimed that he invented algebra, but he might not invent it as well. So I think Leo is right after all. It's kind of improbable that one person invents something like that, but at least we have it there, right? And kind of conceptualization of algebra. And indeed, if you think about Euclid, Archimedes, all these big guys, there is no algebra. It's somehow not in this thinking. You see, you have geometry, you have arithmetic, you have astronomy, you also have music theory, you have mechanics, right? But you don't have algebra. Yeah. No, of course, yeah. No, of course, for saying such things, we should probably define what is algebra, right? Just because we shouldn't talk about name. Of course, name is Arabic, but we should talk about concept. I don't know, what is algebra for you? If you give some definition, algebra. I have kind of answer, I can tell you, but
In which we study objects that are defined by some sort of binary operators.
by what?
Binary operator, like plus and multiplication. study those
But plus is not an object, right?
operator.
Right, right.
Binary operator.
No, so kind of my idea of that, and I think it's more or less what Rushdie is saying about Al-Khwarizmi, and what we'll find there is exactly this, that this mathematic of, say, Euclid or Ptolemy or whoever from this company, it's kind of about, we may call objects, better say probably essences, right? Whatever they are. Are they abstract or they are kind of entities? It's philosophy, right? Different question. However, arithmetic is about numbers, right? Geometry is about, say, figures. That's, by the way, important thing. They didn't really have idea of space. So they might have had it, but rather in philosophy, not in mathematics, right? So in mathematics, we are talking about objects, figures in space, but space itself is not a subject matter in mathematics. Right, these things. However, here we have idea that what is central is not really, roughly speaking, if you like this, I would say entity, or let be object, but operation. And that's very, very different view. And by the way, there is also very interesting comment in Proclus in this commentary. And this comment actually, no, officially this commentary does not extend to the fifth book, to theory of proportion, but actually it's an introductory part, it's about theory of proportion, eudoxus. So Proclus says something like this, that eudox is wrong, saying that kind of foundation, what takes things together, is a proportion. Yeah? Apparently, that's interesting. We don't have much of that, right? But apparently, Eudox, or maybe some of his interpreter, put forward that kind of argument, right? Because proportion kind of works similarly for numbers and for geometrical magnitudes, we would say, even not identically. There is things with having to do with irrationality, we would say today, right? But anyway, for Proclus, and then part of that, his own opinion, Proclus' opinion, right? He says, and Proclus tried to be Platonic. He described himself as a Plato's follower. So he says that's wrong, even if operations are similar or even identical in some sense, right? It's not a sufficient ground. It does not justify the idea that you may develop somehow this theory of proportion as a single theory, right? And actually in Aristotle, there are also similar arguments that you still need to, and this is what we find in Euclid exactly. So separate theory for numbers and separate theory for geometrical magnitude, even if these theorems, they kind of repeat each other in certain cases. But they would say, no, what, so what? It's at a certain point, it's similar, other it's not, but it's still not a reason to develop anything like single science. There are very, no, we don't have time, unfortunately. There are many very neat points in Aristotle also about this. However, in Al-Khwarizmi, we find exactly that. He does that. So we'll see. And with, say, Descartes, who actually, I think Descartes is absolutely singular in the sense that he still is more philosopher than mathematician, right? If you compare with Fermat. And what he did in mathematics is actually kind of philosophical project. And in many cases, it doesn't work. If you have some philosophical ideas and you try to do mathematics alone, it's actually rarely works, sometimes. But Descartes succeeded. I think his geometry, as we'll see, it's a hugely influential mathematical text written completely as a part of philosophical project. And so Descartes, if you want, gives a full philosophical justification for that approach, that roughly speaking, what is central is operation rather than whatever objects you have, you operate with. All right. Now let's talk about this next week and try to read at least a little bit of algorithmy and Descartes geometry. And also I include kind of Descartes philosophical text, but that's if you have time. But even, you see, Descartes' style is it's not like scholarly writing, it's kind of essay, it's like fine literature, so you might enjoy it. If any one of you read French, no? Then it's also very important for French language, I think. It's a really good example, it's very good French. Okay, so. You have some questions and about your papers and essays, please think. And
when is the deadline? When is the deadline for choosing topic? Deadline.
Deadline, yeah. That's. I think it's now we are 5th week. I think, right? Or already 6th. Okay, I stop it.